will talk about perturbation theory for Trojan motion.
Okay, well, good morning to everyone. Welcome here. The people that is not from Vergata, I am, well, as Carlos said, Rocio Isabel Paez. I am from Argentina. I am doing the PhD here. I am so sorry for not being able to do this in Italian. I think I should, but my Italian is still very poor, so well, my apologies for that. I hope I do not speak so fast that you will get lost just by the English, but I will insist to, I will try to keep it very, very slow, or as slow as possible. My work, you will see that is extremely applied, probably much more applied than you are used to, because we are working in a group of astrodynamics in Vergata. So essentially we mix a lot of physics with some mathematical studies, and what I am going to present today is the more mathematical part of my work that, let's say, collects numerical experiments and analytical developments, but well, I hope you enjoy it. So, as a starting, I will refer a few tools that probably you all already know, but I just will introduce the notation because I'm using it a lot. I think most of you have following courses on Mechanica, in analytic mechanics or celestial mechanics or similar, so I will introduce the Hamiltonian formulation again, but extremely briefly. And I will introduce the system because probably you are wondering what the Trojans are. It's a very particular kind of body that we have, for instance, in the solar system, and I will show what it is and why they are interesting. And then I will explain a little more technical points of my own work. Okay, so I start. Probably you know what is a Hamiltonian. It's essentially a function that takes place in a phase space, and it depends on canonical conjugate coordinates. Essentially, physically speaking, it represents the energy of the systems in terms of the kinetic energy and the potential. And it is extremely nice to formulate it this way, because if we want to know how the system evolves, we just have to integrate the so-called equations of motion or Hamiltonian equations. That involves essentially the derivatives with respect to the canonical coordinates of the Hamiltonian. This formulation is very nice, and if we are able to express this function called Hamiltonian just in terms of one of the sets of the variables, the momenta or actions, the system is very easy to integrate, because if we recall the form of the equations of motion, to integrate the Hamiltonian which just depend on the action that we call capital A, is essentially trivial. The other conjugate variable will evolve linearly, and the action will be constant forever, or let's say all my time that I will consider. I emphasize this because this is what we call, in just one of the very heuristic definitions, that the system is integrable. If I am able to take a Hamiltonian that depends on all set of coordinates that I showed before, and I can transform it in such a way that I obtain something like I have above, my system is essentially solved. I know how it will evolve in time. So to get something like that is the aim of many of the dynamical studies that use Hamiltonian formulation. Of course, if the system is not integrable, like we all know that most of the cases are not integrable, what it will happen is that I will not achieve to do so. But I can get very close to that, or to emulate my Hamiltonian with that kind of expression that only depends on the actions, in such a way that can study that and say, okay, it's not exactly my original system, but it's very like. So I can develop and to play with it that is much more easy to understand and to decompose. And well, I can move on with my dynamical study. I emphasize this point here because it's essentially what we do. We take a Hamiltonian that is complex in a system that I am going to introduce a little later. We transform it subsequently, doing a normalization procedure, and we obtain another Hamiltonian from which we can withdraw much more information than in the original case. Of course, this process cannot be done just by chance. I mean, the way of doing it is quite strict, and these are the tools that I am going to introduce next. For instance, just to recall and to give the notation, we have the Poisson brackets that involves essentially the derivatives with respect to the canonical coordinates. That in a very short notation, we can refer to the derivative. If particularly we want any kind of dynamical variable, which essentially is a function that depends on my conjugate coordinates, I know that this variable will evolve. Let's say the flow induced by the Hamiltonian can be written in terms of the derivative computed with respect to the Hamiltonian function that is defined in my system. And well, essentially just to introduce the derivative operator because I'm going to use it quite often in the presentation. I said some time ago to pass from one Hamiltonian to another doing transformations. the Hamiltonian formulation is something very robust. Okay, so if I want to transform to another Hamiltonian, I have to be sure that the new variables are still, let's say, representing the Hamiltonian formulation, that the equations of motion are still valid, and so on and so forth. I cannot change variables just because. I have to control that the transformations are canonical. Essentially, the definition of a canonical transformation is that maintains the Hamiltonian structure. One of the ways of doing it is computing the fundamental Poisson brackets, which is essentially seeing how are the Poisson brackets of, let's say, the derivatives of the old variables and in terms of the new ones, to check that these rules are holding, and I say, okay, my transformation is canonical. I can pass from one set I and phi to another set I and phi, which is different. And if this holds, I will be happy. If you think about changing many times, this thing is not efficient at all. Because I cannot just propose a canonical transformation to check if it happens, if it doesn't happen, change it, try again, and so on and so forth. We would like to find a way to introduce canonical transformations in such a way that by construction are canonical. So no matter what I am using, I know already that they are going to be canonical, and I can still be talking of a Hamiltonian function that is still a Hamiltonian function. So not to spoil the formulation in between. And for this, it's extremely useful to introduce the canonical transformation by Lie series. Maybe I'm going a little fast. Okay. Let's suppose that we have a dynamical variable he, that is the one that looks like an x there, that depends on my conjugate canonical variables. Any of them. If we want to compute the flow that is induced, like if that function was taking the place of the Hamiltonian, essentially we have the Hamiltonian equations applied to that function. It can be proven that if I consider an initial condition and I integrate these equations of motion up to a certain time t, which is generic, this mapping that jumps from the initial condition to the new set of variables is canonical. This can be proven, I will not take here. So essentially, if you think, okay, I have a chosen arbitrary e, I change this value of time, essentially what I get is a whole family of canonical transformations induced by this function he. So if I consider different times, I get different transformations. Essentially, this is not very easy because he is arbitrary, so it can be very complex to compute the derivatives, maybe not easy, and furthermore, it's not easy to integrate those equations. But if, let's say, t is not so big, this integration I can assume it to do it by a Taylor expansion. Okay? Where essentially the only thing that are involved are the derivatives of the variable that I am transforming and powers of t. The convergence of this series is a matter of, well, it's a matter of big discussion, and it is very different of what I am going to say. But let's assume that this is convergent at this point, okay? So my approximation is nice. And in particular, it is convergent for t equal to 1, so I can get rid of the dependency of this parameter, okay? I'm just replacing. So essentially, I am saying, okay, I have a transformation written in terms of a series that jumps from my own variable to the new variable, which has the little 1 on top, and it is written in terms of the derivatives, okay? Which is canonical. So I know already that it's canonical. So, as for the thing that I said before, I can read them in terms of Poisson brackets or Lie derivatives. And in fact, I can generalize the formulation of the Lie derivatives for higher order derivatives, like the derivative of the n, and replace it. Essentially, it's just a replacement, nothing else. This is still canonical. It's passing from my old variable to my new variable, just applying this correction. Just to shorten the notation, I can introduce a kind of exponential operator and read it shortly because it's an infinite series. Okay? Of course, whenever I do so, this series is infinite, but I will truncate it up to a certain order, and I will assume that it's still holding. Okay? It's an approximation. Okay, so I have all variable, and I transform by canonical transformation to a new variable. And this is by construction, sorry that I repeat the words all the time, canonical, okay? But this is what I mean to guarantee. You say, okay, there are many transformations that are canonical that will still keep the Hamiltonian nature of your formulation. Why to introduce something that is so complicated? I mean, it's an exponential series, I don't think derivatives. Well, For the people that work making analytical developments in computers, there are some things that are very nice to have from before, let's say, before we start working. And in particular, analytical transformation by Lie series had many, let's say, good points at the moment of go and write in an algebraic manipulator the thing that you want to do. For instance, I was speaking before about an arbitrary he function, okay, that is just a dynamical variable. The fact that it's arbitrary is incredibly good because this means, okay, I can choose wherever he I want. But in particular, I can choose a he that it will induce in the Hamiltonian that I am going to obtain the thing that I want to obtain. So somehow I can rule the way that I choose the function he in order to obtain a particular result. And this is actually the thing that we will exploit the most. Furthermore, since it is this exponential series and so the Taylor series, if he is not extremely big quantity, the transformation is so-called near identity because essentially keeps more or less what was the original value and some corrections of higher and higher order. This allows us not to lose very much on the control of what the variable is truly meaning. For instance, let's say that I have a variable that is a velocity, okay, and I use this kind of transformation. The new variable essentially will represent a velocity with small corrections. It will not be something completely different, okay? This is the key point of the near identity when you try to think physically what you are doing on the formulation of the problem. Well, furthermore, it's just involving Poisson brackets that are derivatives that are extremely easy to deal with in a Hamiltonian formulation, in particularly if we are expanding in series that are polynomials. The derivative of polynomials are trivials, and we like that. Well, to compose this kind of operators is extremely easy. But furthermore, I can deal with the transformation of individually each variable that I have of my system. Let's say at the very beginning I introduce that the phase space is n two-dimensional, so I can have many dimensions I want. I have a pair of conjugate variables. If I need to change some of them, I don't necessarily have to affect all of them. I can just take the transformation of these two and go on as far as I need, and not to change nothing else of the variable that I have in my system. Okay? So these 3 or 4 points are crucial for the development that we are going to do afterwards. Okay? Well, this was just the tools. Now I'm going to talk about the Trojan. Probably you all of you know what is the two-body problem. It's something that is integrable, is solved very, very, very long ago, and essentially implies the motion of two bodies just by gravitational force, one around the other. We know by Kepler that this problem has a solution, and in fact is what he discovered for the solar system, that the motion are ellipses with the big mass in one of the focus, or essentially in one of the focus, and the other one orbiting around. And if you want to represent the motion around in that ellipse, essentially what you have to do is to define the shape of the ellipse by giving the my-axis and eccentricity, that is just telling how the ellipse looks like. Then to locate your ellipse in the space by giving the inclination, the latitude of the ascending node, and the argument of the perihelion, horizontal, with respect a frame of reference that is essentially defined by us. And after we have located the ellipse, we only have to say, okay, where is the body around, let's say, on that ellipse? And this is given by mean anomaly, which is an angle. I do not explain very much what are these, but I introduce the symbols because I will use it in the formulation. The variable that we are going to use depends on these elements, so just to be for completeness, essentially. Well, what is a Trojan body? The thing that I showed before applies for a two-body problem. If I add a third body, well, first the problem is not longer integrable. Okay, this is what demonstrated long ago. But if we assume that we have a big body, the second body is big, but for sure not so big like the first one, and there is a third one that is extremely, extremely small. So essentially, the motion of the two bigs is going to be given by the solution of the two-body problem, because the third one is not doing anything, but for sure the third one is going to be affected by the things that are happening with the two bigs. So this problem, that is very well known and very genetic, had 5 equilibrium points for the motion of the little mass, that is the one that we are interested in. The 3 collinear equilibrium points are unstable, and we are not very interested in them right now. But the two equilateral, that they are equilateral because they form a triangle with respect to the position of the big mass and the smaller mass, for certain values of the masses of the planet, are stable. So this means if I am here and I kick a little, the guy will stay rounding this border and so on. And this is trapped in a certain stability region. You can say, okay, this is very heuristic, but how you can apply this to something truly real? If you go to a solar system and you consider, well, probably you can see, if you consider the problem given by Sun, Jupiter, and some little negligible mass, you find that here is L5, or L4, sorry, and there is L5. And these regions, truly in the space, are full with asteroids. So there is a stable region, and these guys are trapped. And as long as my system evolves, imagine that Jupiter, of course, is turning around the Sun, these guys are leading or following the motion of Jupiter. They are there, they are observed. Furthermore, the people, since they discovered the first Trojans, these are called, sorry, they are called Trojans, this is why they are Trojan bodies, they tried to emulate numerically if they guys were truly going to be there for a long, long time. Numerically speaking, the people just take the physical system, derive the equations of motion, probably Cartesian coordinates, doesn't do anything, compute numerically, obtain the result, and say, okay, you have like 10,000 asteroids for each point that are going to be trapped there forever. Then, people doing analytical studies say, okay, we would like to prove this stability, formally speaking. We have on dynamics the so-called stability theorems, like the KM theory, Kolmogorov-Barnard-Moser theorem, or the Rocio stability theorem, that will allow us with certain tools and developing some Hamiltonian for the motion to understand if these bodies are going truly to be trapped there. The truth is that when the people try to do this work analytically, they say, okay, of your 10,000 bodies that numerically you are telling me that they're going to be forever, I can justify it for 12, 13. So the difference was huge. And for many, many, many years, the people was wondering, okay, what we were doing wrong. I mean, it is not just that the problem is analytically complex. We may be choosing some things wrong in our development that may be improved, and we may obtain better results. In this, there are 3 points that ourselves we are somehow correcting of this approach that I will introduce in the next few slides. But essentially, this is what we are trying to get. To provide a better Hamiltonian for the motion of one of these generic problems that will improve afterwards those results. And they are basis in the fact of the tools that we are using, like the B-series, and some physical concept that we know already for the system and we would like to apply. So, we are going to talk about the Hamiltonian of the Trojan, essentially. If we have the 3 masses, the big one, the smaller, with respect to the big one, we call it primary, and the very small one that we are going to study, the Hamiltonian of this function essentially is the kinetic energy and the potential, and it can be arranged in such a way that this represents the motion on an ellipse. Let's say the influence that just exerts the big mass, the star, plus a perturbation. This mu that we have here is a mass parameter, the so-called mass parameter, that is essentially the ratio of the primary mass over the star. It's a small value. So this Hamiltonian from the very beginning is telling us, okay, you are going to be moving essentially on an ellipse with a perturbation. So almost an ellipse. If we remove this guy here, that is this function R is called the disturbing function, the problem is trivial. It's an ellipse. There's nothing interesting there or nothing that we do not know. This guy here is the one that gives the whole relevance, the whole complexity and the interesting point of this work. So I am going to emphasize a little more what we do here than what we do on the rest. Okay? Just for completeness, if you use this vectorial notation that we can see in the plot, what we get is this Hamiltonian, and the disturbing function in between parentheses is composed by these 3 terms. Well, the first change of variables, there are going to be many. 2 important, but many. The first thing that we have to do is to transform to something that will allow us to understand the problem a little better. And this will introduce the canonical coordinates, which is a very well-known set of canonical coordinates that essentially are the action angle variables This means that a certain Hamiltonian in terms of these variables, it just will depend on the actions for the two-body problem. So if I would replace here, in the part that was going to the ellipse, I only have the action G and gamma that essentially depends on the value of the major semi-axis of the ellipse and the eccentricity. These are variables, they change in time. Don't forget it. Now it's not a fixed ellipse, it's an ellipse that is evolving. And of course, something we will do with the disturbance function. We will extend the phase space in order to get rid of the explicit dependence on the time, and we will introduce a new angle, essentially a new degree of freedom. But essentially, this is the important set of variables that we are going to keep for the rest of the presentation, that are depending on essentially rho and c, that are the new actions, that essentially are related with the major semi-axis and eccentricity, two angles, and well, of course, horizontally you have the conjugate pairs, rho and tau, c and eta. Our final Hamiltonian is going to be something like that. The Keplerian part is transformed exactly like that, and something will happen with the disturbance function. Roughly speaking, if we have the still Vergatian expression for the disturbance function, where the primary is located in a certain point, given by that, the other one will be, let's say, refer like a distant air to the star, and a certain angle bar theta that is going to be extended between the primary and the small body. Well, the disturbance function acquires this shape. So essentially what we have to do is to translate these three terms to my variables and to see what happens. The first one may look a little complicated because you say 1 over R will be equal to 0 in a generic problem, but not for the Trojans, because the Trojans are trapped in around L4, and L4 it is always to a certain distance to the star, so we cannot approach very much to the star. This time will not generate any kind of problem, and the only thing that we have to do is to replace the dependency of R essentially in terms first on orbital elements, which is what I introduced here by using the Bessel function that are the J's, and then to pass it to my variables that I need. In this case, are just appearing rho, c, and eta. The last one, tau, is not appearing, which is the angle. The second term has a little dependency with the angle, but essentially is trivial to replace with formulas that are very, very well known in celestial mechanics. I will emphasize this point here. F1 and F2, let's say two functions that I obtained for each expansion, essentially keeps this shape. Are polynomial functions depending on rho, c, and eta, certain coefficient, and let's say the cosine of tau or sine of the tau to a certain power. This is what I am emphasizing. If we have this kind of function, computing the derivatives by the Poisson bracket and so on is very easy. It's truly very easy. So this is why it's useful to use the derivatives. There is a little problem with the third term. The third term is given by that expression over there, which essentially what it means is this instance. Okay? The problem with that is that my body cannot go very close to the star, as I say. But we know, because we have integrated numerically what happened with the Trojans, they can do something very wild, angularly speaking, okay, in this sense. They can approach very much to the primary in this sense. And that term becomes singular, okay? I have a denominator equal to 0. So you say, okay, but if you don't touch it, essentially your series, if you are going to expand this by series in terms of your angle tau and so on, you will do it, yes. I mean, I am still inside my domain of convergence, but if I am going here, I will need such a long series that truly will represent correctly the motion that this thing becomes useless, okay, to expand around that. I will make a little remark at the end of the presentation about that. So, this term is the one that generates problems. When the people was trying to make something like that, for making a series of this way for that term, they were needed such an amount of terms that this thing was truly not helpful. And if you have to truncate your series in more or less coherent way with respect to other functions, all the thing becomes a mess. And essentially, this is why essentially the results, the analytical results for the stability domain were failing so far. But we will introduce three hints. Let's recall the Hamiltonian, the part of the Hamiltonian that was associated to the ellipse. I say, okay, this gives me the ellipse, this gives me a certain small correction to that motion on the ellipse. So I would look that part of essentially the biggest. We can, if we compute the equation of motion in the first set of variables that I show because it's more clear, we will see that one of the angles has a frequency equal to 1 and certain corrections, and the other one has a frequency that goes with this small parameter mu. So by just the way how we describe the Hamiltonian, we see that the two angles that we have for the 2 degrees of freedom, one is fast and the other is slow. And since we want to study the long-term evolution of the system, the fast angle is not very interesting because essentially we give a kind of noise on the evolution of the other one that is going to be the slow, and essentially a long-term period will rule the motion. So this way of writing, and this is why I choose these variables in the beginning, allows us to distinguish between the 2 degrees of freedom, one is going to be fast and one is slow, and then to design a normalizing procedure for the Hamiltonian that will just depend on the slope. Also, I will remove the dependency on the fast degree of freedom. And this is the second point. Furthermore, since I am using this series, I can choose this function he in order that my normalization is going to move forward by trying to accomplish this. Okay? So these 3 points design somehow the idea of which kind of normalization we are going to keep. And for doing so, okay, you can say, okay, but the term is still problematic. No matter what you want to do, the term has the problems. Okay, but since I am going to average over the other degree of freedom, the one with m, at tau, my angle that may be generating problems, I can keep it in a kind of soft way, a more complicated way. But this will not generate any problem in the normalization scheme. And in particular, what we do, the strategy what we do, is to create an expansion, essentially, where I still keep the polynomial dependency in the cosines and sinus, but I also have a function of tau that keeps this weird shape, that essentially the one that is generating the problems, that I will not touch it. I will only have terms to this power. I will anyway go to a normalization scheme. Everything will work fine, because essentially I am not averaging over this guy. This guy is going to be untouched. So, essentially, my final Hamiltonian, I will speed up. My final Hamiltonian is, well, the series of terms for the Keplerian part, and this kind of guy. So, polynomial, cosine, sinus, eta. Okay? Well, so far, so good, just change of variables. Now we enter truly with a canonical problem, let's say, to make a set of canonical transformations that is going towards the Hamiltonian that we want, that just will depend on the slow degree of freedom. This is just a rough definition for introducing sense to this formula, but essentially what we design is a scheme that at any moment on the iteration, in other words, how does it work? I have my initial Hamiltonian. I transform once, I have another Hamiltonian in a new set of variables. This transformation has to be canonical. Then I transform again, and I transform again, and I transform again. After a certain period, what I will have is a Hamiltonian that is accomplishing certain rules that I am looking for. Okay, this is what I achieve with this series. So this is a generic intermediate point. What I will have is a normal form, that is the part that I already transformed, that is already has the shape that I want. Some terms that are in the process of normalization, and some terms that I didn't touch yet, okay, for higher orders of mu. The way that the exponent, what we have here is the rule for the exponent, but it's completely what I am saying here, and how we guarantee that we are doing so, not just by saying the thing will happen this way, by construction. This is how I use the Lie series. I define that my new Hamiltonian, or the new Hamiltonian in a certain step, will be the exponential of the derivative applied to the previous step Hamiltonian, where this function he is obtained by solving a homological equation. And by construction, the homological equation is using a circle kernel that will guarantee that up to a certain step, it will kill, between quotes, it will kill the term of the Hamiltonian that we don't want it to appear, and it will retain the things that we want to keep. So essentially, by applying this subsequently, the set of generating functions will kill the fast degree of freedom. At any moment, or any iteration step, my normal form are given by this structure. Will depend on tau and rho in a generic way, but C and eta are going to appear to the square and divided by 2. Essentially, this if you probably don't recall already, it is the first thing gamma, the first variable gamma that I found that will be essentially an integral of motion, because the conjugate angle will disappear. So, well, at any point, the normalized Hamiltonian, at the end of the iteration, let's say a maximum degree of normalization that I want to keep, that is arbitrary, it will probably respond directly to the computer that I have, or the problem that I truly want to solve, will contain this part and a remainder. As smaller the remainder, as better my normal form with respect to the original Hamiltonian. This is the correction. Essentially, we should do this up to the point that this is minimum. This is the criterion. Essentially, if it depends which software you are using, this is not so easy to achieve, because maybe you have to do this step 50 times, 60 times, 100 times. So essentially, we just look at it. We decide an arbitrary order and we look at it there. If you study the Hamiltonian, the original Hamiltonian, like it was our normal form, we can see that for the equations of motion, that okay, rho and tau are the slow degree of freedom, and it is free, it will do whatever it wants to do. But gamma, since the conjugate angle is not there, in the equations of motion, the derivative is equal to 0. Gamma is a constant. Okay? So essentially, by this procedure, we keep not gamma, but the degree of freedom. So, the results. Because from here, everything very nice. Does work well. This is a numerical integration. In red, what we have is what happened in a surface of section if we integrate the very first Hamiltonian in Cartesian coordinate that I showed, that was depending on R10, R20, and so on and so forth. If you shall put this in a numerical integrator in the computer, you let it evolve, and we obtain the red pures. Am I saying correctly? No, sorry, the blue pures. Okay? The red pures is exactly the same when we put the equations of motion of our Hamiltonian. So if you can see, this is L4. This is an orbit that are trapped around L4. This is a so-called horseshoe orbits that go also around L5. But for the same initial conditions, the behavior of our Hamiltonian and the true Hamiltonian, or the complete Hamiltonian, is extremely good. Extremely good. And in fact, this thing that is able to reproduce the two different kinds of motions and angles that are displaced a lot here, if you check all these guys to pi, so there are things that are truly making big excursions and speaking, well, the result is extremely nice. This is done for the Earth-Moon system, for the Sun-Earth system, that has this mass parameter mu extremely small. If you compare the mass of the Earth with respect to the Sun, well, the ratio is very small. It's like 1 millionth part. Okay, so there is essentially the amount of chaos that we have there is very small. It's kind of two-body problem. Just the influence of the star essentially. If you pass a little more complex problem, like the case of Sun-Jupiter system where the mass parameter is higher, the relation of colors is the same, the blue is the complete problem, the red is ours. You can see that, let's say, the curves, the orbits in this system are truly well located. But of course, for integral approximation of what degree of freedom, it's not truly able to reproduce the chaos. I don't know if you can reach to see, but there are many blue points over there that are the orbits that are becoming chaotic in the complete problem, and we truly cannot represent. And also we have some secondary resonances that doesn't matter what they are, but we cannot truly emulate the islands of instability because our problem, let's say, is not due to do so, but it's extremely able to locate very well. So at this point we are very happy because there are many motions in this domain that our Hamiltonian is able to reproduce correctly. The next point would be to give this to someone that is truly working on the study of stability of these problems. Say, okay, I have a new Hamiltonian. Try your theorems again. Try to study stability. And let's see if it gets a little better of what it was before. I will not do it because I don't have time in my PhD, but I hope someone will do it in the short term. And before finishing, sorry if I'm talking too much. I will introduce something which is a slight modification, because I say, okay, you have a singular point in your problem. You have this 1 over the square root of lambda that is generating problems. You say, okay, if you need to expand, the best thing that you can do is not to expand. This is not a solution if you truly need an expansion in this way. In general, what the people does or was doing long ago is to say, okay, I truly need this guy. I truly need something that it is a polynomial along the variables of my system. the thing that I'm going to apply afterward needs this feature before. So I cannot avoid it. You cannot tell me, okay, keep the square root because this will not solve anything. So, in general, what the people want to do is say, okay, we will take the equilibrium point, we will expand around there, which is equivalent to pi over 3. We will make the series of the cosinus, we will make the series of the sinus, we will make essentially a series for this beta that I introduced before, and I will go on. But beta is still having the same problem as before. This series, for being truly meaningful, I need to keep such an amount of terms that it becomes very, very bad. Essentially, because the convergence domain is relatively small. So what we propose is, okay, let's not expand around pi over 3. I mean, it has a lot of sense to expand around the physical equilibrium point, but let's not do it. Let's expand around other points. Let's say pi over 2. We have to go up to the first singularity to have the convergence of the domain. So we have essentially to go up to pi over 2. My domain is essentially altogether much bigger. Since we still need to refer to the equilibrium point because it's what essentially our variable means, then we will swap again. So essentially, my series is going to be a Taylor series, but the coefficients are going to be different. The key point is, it is better. I mean, solve something. Well, a little light. But this is the numerical integration of a complete problem, exactly as the one before, but with a different mass parameter, which is much bigger. The main feature that you can see here, besides, let's say, all the orbits around the equilibrium point, is a huge secondary resonance that is extremely nice to study. So this is fully numerical one. If we compute what happened with the Hamiltonian before normalizing, let's say, just considering these two schemes of expansions that we use, we have two results. This is the one with the so-called asymmetric expansion. First expand around pi over 2, then moving to pi over 3. This one is directly expanding everything and referring everything with respect to pi over 3. You can say, okay, this one, in all this part is very nice. This one, maybe this island of stability does not have the correct shape and so on and so forth. The problem with this one is that I cannot pass this border. Let's say, my series expansion for the same amount of terms in the two cases, very quickly it fails, and the numerical integration starts failing to get truly the orbit and so on and so forth. So whenever is happening here, that in the true problem, let's say, something is happening, with that expansion I cannot recover. And this is the problem that we were saying before. For this feature, essentially, when the people want to approximate, to study analytically, the orbits of the Trojan that are not so close to the equilibrium point by far, they cannot do it because of this fail. So there is no analytical development that you can work here. But if you make the other trick, that of course, probably to recover the correct shape, you have to use a little more terms, but not so many, you can go much farther in the study. So essentially, if you need to do something that we are trying to apply now, which is computing a resonant normal form, that you need to have truly the whole set of parameters, the set of polynomials, this expansion doesn't work, and that what it does. And actually, for instance, it's able to recover analytically these islands if you do the things correctly. Okay? So just for finishing, because I'm passing the time, to emphasize that even very, I don't know if silly, but kind of trivial tricks from problems that are very old could solve many things. And all these results were very promising. We were very happy when we obtained it. So we will move on to see if truly we can get at least 300 stable Trojans analytically speaking. So that's it. Thank you very much.
Questions to the speaker? So I guess also from what is observed, the intuition would be that one should obtain that they are really stable. This object is somehow a shortcoming of the analytical tools until now.
Yeah, at least for long term, but the problem is truly complex. I don't believe that we are ever going to contain the whole domain, but the previous results of the stability domain were very small, truly small. I think the best achievement was 10 years ago for applying the KM theory, the theorem to that, and it gets 35, I believe, something of, there are 10,000 bodies around each point, so But essentially, the problem with this way is that they're very far. The true orbit is, let's say, quite distant from L4. They're supposed to be trapped anyway, but making very long terms, so they are difficult to catch for this. And I don't know if someone had applied this for the Trojan of the Earth. The Earth has a Trojan body, just one, so far. And I think they were trying to implement this, but it also has a very open orbit, so I don't know. It may work.
Can I make a comment? Yes. No? Yes?
Yeah, sure.
Yes. So first of all, you are very generous because it was not only 10 years ago, but this is a long-standing question which dates back.
The last work, yeah, I think it was more or less 10 years
last
ago.
work, okay. So, but the first work was at least 30 years ago.
Yeah.
And the difficulty is that when you face a problem like this, that is an astronomical problem with the real bodies, and then you want to apply the analytical theory, then you have to match between the mathematical problems, that is the estimates which come from the mathematical, the analytical estimates, and the real problems. And this is a very difficult problem that people tried to do in the past years. There were some works by, if I remember well, by Giorgini, and then Giorgini and myself, and then Skopos, and then Christos Septimiopoulos, and so on. And all these estimates were able to catch just one body. And one body was a big success. That is, when you have estimates which fit with one asteroid, one Trojan asteroid, you say, hurrah, it's a big result because your theory, the mathematical theory, is able to match one body. So to have results which cover a wide spectrum of bodies is really nice, at least from the astrodynamical point of view. And besides this comment, I would like to ask you a question that is whether you, in your work, you also computed which is the optimal order of the Birkhoff normal form.
No, I didn't reach
your computations really to the limit of the mathematical side, or
no, because it is more or less known what could be, let's say, an optimal order, because there are many works in this field. But the thing is that myself, I am doing everything with Mathematica, which is a symbolic manipulator, and it looks very nice. But if you want Mathematica to compute a normal form up to order 30 or 50, at least my computer crashes in between, so it doesn't hold. I should use a different tool to truly try to approximate the things better to an optimal order. But I haven't done it before. Actually, the pictures that I show here are for a very small order of normalization. I think up to 5 or 3 or something very, very short. So the results are even good, even if you don't go so far. Technically speaking, we should go further. And I will make a comment with respect to what you mentioned before. It's true, this work that people start dealing with like 30 years ago, maybe more, about Trojans is something that started in the 60s. And some of the points that I emphasize, like the use of Delaunay variables and so on, they are achievements that the people have done a long time. Let's say it's not that I myself I impose all together. Some works are improved because instead of using Cartesian variables or polar coordinates, they already introduced Delaunay variables and the results were a little better. What we are doing is collect many different, let's say, contributions and to get something that seems to be truly better. So let's hope that it truly works afterwards.
Okay, if there are no other comments, then let's thank again our speaker.